Hi guys, welcome back. I hope you had a good weekend. So far we have seen all the tools of algebra and calculus that I think are going to be useful for the applications of that we're going to look at in this class and that we're going to look at in your research. So today it's lecture 6, and what I would like to study together is how to draw the graph of a function. Some of you might be familiar with it. Some of you might have seen only simple functions. So I'm gonna explain a major classification of functions that we might deal with, and then we're gonna look at some examples. So again, a function is essentially a relationship between two variables in the form y equal f of x, which means that we take any value of y that we want with some limitations, and then we're going to associate a value of y. So we have our Cartesian plane. Here we have the x-axis. Here we have the y-axis. And here we can define any relationship that we want, y equal f of x. So for each value of x, we're going to associate a value of y. Now, x is the independent variable. And y is the dependent variable, because it depends on the relationship that we define between the two variables. In general, we're going to look at functions from the set of real numbers to the set of real numbers, so functions in one variable. And it's important to define the domain of a function, because it's true that you can, in theory, assign any value of x that you want, but the function has to be defined. So the domain of a function is the set of values x such that f of x is defined. What do I mean with that? Well, if we take, for example, f of x equal the log of x, well, now x has to be positive, otherwise the function is not defined. So the domain is all the x's in the set of real numbers as long as x is greater than 0. So when we plot the graph of the function, essentially all the values in the negative part of the plane cannot be assigned to the function itself. So then we're going to have our logarithmic function that looks like that. So only the positive values of x can be assigned to the function. Then if we take f of x equal 1 divided by x, again, x cannot be equal to 0 because otherwise the denominator is not defined. So the domain is all the x's in the set of real numbers such that x is not equal to 0. Okay, well, there are several ways to classify functions, but the one that I like the most and that I think it can be more useful for us is the following here. So we have two main set of functions, and in each of them we're going to have subgroups. Now, the first group includes all the rational functions and the irrational functions. This includes operations that you can do with algebra. And then we have the group of logarithmic functions, exponential functions, and trigonometric functions. These functions here cannot be expressed as a combination of a finite combination of algebraic operations. So examples of rational functions. Well, all the polynomials, so y equal ax plus b, y equal ax squared plus bx plus c. You can also put, well, essentially any polynomial, say in the form n x power alpha, or well, let's say alpha times x power n plus beta times x power n minus 1, and so on and so forth, plus delta. But we can also have fractions of polynomials, so functions in the form ax plus b divided by cx plus d. These are still rational functions. Now, for these functions here, we have to be sure that the denominator is not equal to 0. So for these functions, the domain is the entire set of real numbers. Whereas in this case, we have to define with fractions in general, we have to specify the denominator cannot be equal to 0. So in this case, the denominator cannot be equal to 0. Then we have irrational functions. So functions in the form y equal 4x minus x squared, y equal cubic root of x squared minus x plus 1, y equal fourth root of x minus 2 divided by x squared plus 4. All these functions are irrationals because there's a root somewhere, either a square root or a cubic root or a root with a higher order. And again, we can have fractions of inside a root or not, but all these functions are irrationals. Then we have logarithmic functions. Well, functions in the form y equal log base 2 of x, y equal x times log of x, y equal 1 divided by log of x. All these functions are logarithmic because there's a logarithm in it. Exponential functions, so functions with an exponential expression, y equal e power x, y equal 4 power x, y equal x squared times e power x, 1 divided e power x, and so on and so forth. And then we have trigonometric functions. These are just examples of functions that we might see in the class. Well, this is straightforward: sine of x, cosine of x, y equal 1 divided by cosine square of x minus sine of x. So if we have a fraction, we have to impose the denominator is not equal to 0, and then we have to study the domain of the functions based on how the function looks like. You might have other classifications of functions that might be useful in some cases. For example, odd versus even functions. Well, essentially, an even function means that f of minus x is equal to f of x. So it's symmetric with respect to the y-axis. And then an odd function, it means that f of minus x is equal to minus f of x. Which is symmetric with respect to the origin of the axis. So, quick example, if you take f of x equal x squared, this is even. Well, x squared plus c, I guess. Because the value in minus x, the value of the function if minus x is equal to the value of the function in x. And then an example of, so this is even, an example of odd function is f of x equal x. Because the value in x, which is y, is equal to the value minus the value in minus x. Well, then you can have increasing versus decreasing functions. So increasing means that if you have x1 less than x2, then f of x1 is less than f of x2. And then decreasing means that x1 less than x2 means that f of x1 is greater than f of x2. So an example here, f of x equal e power x. This is an increasing function. And the decreasing function is simply, f of x equal 1 divided by e power x. This is the worst graph ever, so let me redo it. Okay. However, we're going to use most likely this kind of classification because it's easier for determining things like the domain, when the function is positive and when the function is negative, and so on and so forth. You can find other classifications like monotonic versus periodic and so on and so forth, but this is all we need essentially for our study. Well, let's try to define some general rules about the domain of a function. So if we have rational functions, in general the domain is the set of real numbers, for example for polynomials, unless you have a fraction. And in this case, you have to clarify that the denominator cannot be equal to 0. So again, if we have something in the form y equal x cubed plus 2x squared minus 5, the domain is the set of real numbers. But if you have something in the form x squared plus 4 divided by x minus 1, then x cannot be equal to 1. So the domain is the set of real numbers except for x equal to 1. So in general, this is valid for a function y equal f of x. But if we have a fraction, then g of x has to be different than 0. Now, if you have irrational functions, well, it depends on the order of the root. Because if you have y equal the nth root of f of x, if n is even, then we have to impose that f of x is greater than or equal to 0. If n is odd, then it can be whatever you want. So d is equal to the set of real numbers. So for example, if you have y equal square root of 4 minus x squared, then 4 minus x squared has to be greater than 0, which means that x has to be between minus 2 and 2. So the domain is all the x in the set of real numbers that are in between minus 2 and 2. it's important the equal sign, because the square root of 0 exists and it is 0. What doesn't exist is the square root of a negative number. Now, if you have y equal the cubic root of x squared minus x plus 1, well, in this case, it doesn't matter. The domain is the set of real numbers, because a cubic root of a negative number exists, and it is minus the cubic root of that number. Now, again, if you have a fraction, you have to clarify that the denominator cannot be equal to 0. So g of x cannot be equal to 0. It doesn't matter if n is odd or even, a denominator cannot be equal to 0 no matter what. Now, if n is even, then the only condition is going to be g of x different than 0. So if n is, sorry, if I think I said it wrong. If n is odd, the only condition is g of x not equal to 0. If n is even, well, then we have to impose that g of x is not equal to 0, and that f of x divided by g of x has to be greater than or equal to 0. So for, again, even root, we have to define roots of even order. We have to impose that the argument of the root is greater than or equal to 0, and if there's a fraction, we have to impose that it is not equal to 0. The denominator is not equal to 0. For logarithmic functions, well, we already know that the argument of the log has to be strictly greater than 0. So if we have something in the form log of base a of f of x, then f of x has to be greater than 0. So for example, if we have y equal log of x plus 2, then the domain of the function is, so x plus 2 has to be greater than 0, so the domain of the function is all the x's in the set of real numbers such that x is greater than minus 2. For exponential functions, it is pretty straightforward, because in general, y equal a power x. This is the set of real numbers. Now, again, be careful when you compose. So if you have y equal e power x, the domain is the set of real numbers. But if you have something in the form e power 1 divided by x, now e is defined no matter what, but here we have a fraction and the denominator cannot be equal to 0. So in this case, we have to impose that x is different than 0. It doesn't depend on the exponential. It depends on the fact that the exponent is a fraction. And then we have all the rules for the trigonometric functions. In general, sine and cosine are defined for all the x's in the set of real numbers. Tangent is defined for x, which is not 90 degrees plus k plus 180 degrees. K times 180 degrees with a periodicity of 180. So we're gonna see these cases if we move forward. Here, I'm just gonna write a short summary. So if we have y equals sine of x or y equal cosine of x, here the domain is the set of real numbers. But then if we have y equal tangent of x, here we have to specify that x cannot be equal to 0 because the tangent is 0 is not defined, plus k the tangent in 90 degrees is not defined. And then we have a periodicity of 180 degrees. So if you want, you can also express it in pi divided by 2 times k plus times pi where k can be whatever you want, of course. Okay, well, let's see some examples. So we're going to get a little bit practical here. If we have y equal x cubed plus 2x minus 5, again, this is a polynomial. The domain is the set of real numbers. If we have y equal x squared minus 4 divided by x plus 3, now here we have a fraction, so x plus 3 cannot be equal to 0. So the domain is all the x's except for x equal minus 3. We have y equal square root of, so I'm going to write 2, although it's not necessary, x squared minus x. Now, this is even, so we have to impose that x squared minus x has to be greater than or equal to 0. Now, this can be written as x times x minus 1 greater than or equal to 0. So this is x less than or equal to 0 and x greater than or equal to 1. So the domain is all the x's such that x is less than 0 and x is greater than 1. So this means that when we define a function, we cannot define the function in this interval here. So this is 1. So this function here is not going to be defined for these values. Indeed, if you try to assign 1 divided by 2, this is going to be 1 divided by 4 minus 1 divided by 2, which is minus 1 divided by 2, and you cannot define the square root of minus 1 divided by 2. So when we plot the function, this is not going to be continuous because it's not going to be defined in between 0 and 1. And it's going to, we can define the value in 0 and the values in 0 and 1 because it's defined. And actually it's 0 minus 0, 0, and 1 minus 1, 1. So the square root of 1 is 1, and the square root of 0 is 0. Now, if we take the cubic root of the same quantity, x squared minus 1, well, here we have the order is odd, so it is defined on the entire set of real numbers. If we take y equal the log, say log 10 of 4 minus x squared, now 4 minus x squared has to be positive, otherwise the log is not defined. So it means x squared minus 4 less than 0, which means that x has to be between minus 2 and 2. So the domain is all the x such that minus 2 is less than x less than 2. I think I might have mentioned it earlier on. Oh, it was a different example, sorry. So again, in this case, it means that this function here is only defined between minus 2 and 2. So if x is less than minus 2, and if x is greater than 2, the function is not defined. So the function exists only in this portion of the plot. Y equal 3 power x. Again, this one here is defined on the entire set of real numbers. Now, there are other things that we can study when we look at functions. In general, I would say that there are at least, let's see, I'm trying to do the math. 4 things that five things that I would like to study every time I look at a function. So I'm going to write the list of things here. So the first thing is the domain. We want to study where the function is defined. It's important to study the intersections with the axis. So if we have a function here, and we have a with x-axis and y-axis. It's important to study where the function is positive or negative. Somehow we would like to study the limits at the boundaries of the domain. And we would like to study where the function is increasing or decreasing. So to do that, we're going to use the first derivative. Sometimes we also want to study where the function is concave or convex. So in this case, we're going to study the second derivative. And if we want to study the area of the function in some specific intervals, we're going to use the integral. We're not going to do that in the examples, at least not today, but this can be something important to do in some applications. Well, for this part, we're going to use equalities and inequalities. So in general, if you have a function y equal f of x, so studying the domain, it means studying the function, the values of x such that f of x is defined. Then we want to study the intersections. So we're going to impose x equals 0 and study the values p equal, in the form p equals 0 and the value of y. And then we want to study where f of x is equal to 0. So we want to study the points in the form x and 0. So this is going to give us the intersection on this axis and this axis. Well, obviously this one here is unique. Otherwise, it's not a function. This one here can have multiple intersections. We might have a function in this form, and so on and so forth. Then we want to study where the function is positive or negative. So we're going to have to solve an inequality f of x greater than 0, or if you want greater than or equal to 0. Well, the equal to 0, we have already done it in the previous part. Then we want to study the limit, let's say for x that goes to plus or minus infinity, or whatever is the border of the domain of f of x. So we're going to be able to study what happens to the function when x becomes very large and when x becomes very small. Well, it could go in this direction or in this direction or converge to 0. But we're going to study essentially when x becomes very big, and when x becomes very small. And then, well, in order to study when f of x is increasing or decreasing, what we're going to do is study f prime of x, the derivative of x greater than or equal to 0. Okay, well, we're going to do some examples. I have 5. I really don't know how long it's going to take, especially because my pen is not really working today, but we're going to try. So let's do example number 1. The function is pretty easy. Is f of x equal 3x cubed minus 2x squared. Okay, this is a polynomial function, so the domain is the entire set of real numbers. We don't have any fractions, so you can assign any x in the set of real numbers and the function is defined. Then we want to study the intersections. So first we put x equals 0. Well, here we just substitute. We're going to get f of x or y is equal to 0 minus 0 is 0. So the origin is one of the intersections. So there's a point P equal 0, 0. Well, then we're going to impose the y of x, f of x is equal to 0, and we want to determine the values of x. So we have 3x cubed minus 2x squared equals 0. Now we can solve this inequality. We can solve this equality in a very simple way. We have 3x cubed minus 2x squared equals 0. We can factor out x squared, so we're left with 3x minus 2 equals 0. Now here we have that x squared is equal to 0, or 3x minus 2 is equal to 0. Now x squared equals 0 means that x is equal to 0, which is exactly the solution that we found before. And then we have 3x minus 2 equals 0, which means that x is equal to 2 divided by 3. Okay, so we know that if we have our Cartesian plane, we know that the function is going to go through this point, and we know that the function is going to also go through this point where this one here is 2 divided by 3. And we know that the function is defined on the entire set of real numbers. So now we want to study where the function is positive or negative. So we have f of x, we're going to solve f of x greater than 0, which means 3x cubed minus 2x squared greater than 0. Well, we have already studied the associated inequality, which is this one here. So this one here can be written as x squared times 3x minus 2 greater than 0. We already know what the zeros of the functions are. So we have to determine where the function is positive or negative. Now, x squared is greater than 0 for all the x's except for x equals 0. And then 3x minus 2 is greater than 0. It means that x is greater than 2 divided by 3. Okay, so what happens is that here we have 0, and here we have 2 divided by 3. Now, x squared greater than 0 means that this function is positive in all the points except for 0 itself. And then 3x minus 2, x greater than 2 divided by 3. We have already solved that. So it's positive here and negative here. So overall, this function is greater than 0 when x is greater than 2 divided by 3, and it's negative otherwise. So somehow we can represent it in the Cartesian plane. Okay, so here we have an intersection, and here we have the other intersection. Now we know that the function is going to be positive here, so it's not going to, the graph is not going to appear in this part of the plane. And then it's going to intersect in 0, and the function is going to be negative in this part of the plane. So somehow the function is going to go to this point, like with it as a tangent, but then it's going to be again negative, and then it's going to intersect in 2 divided by 3. Well, we can study the limits. So the limit for x that goes to minus infinity of 3x cubed minus 2x squared. Well, this is pretty simple because this is going to be minus infinity, which is minus infinity. And then the limit for x that goes to plus infinity of 3x cubed minus 2x squared. Well, you can factor out x squared. So we're left with 3x minus 2. Now x squared goes to infinity, 3x minus 2 goes to infinity, so this is plus infinity. So this means that if I go back to my plot, I know that the function eventually is going to end up here, and it's going to end up here. Now, here we have some sense of how the function is going to look like, because we know that it has to go to 0, it has to go down, up again, and then towards plus infinity. However, we should study when the function is increasing or decreasing just to be sure of the behavior of the function. So the last step is to study the derivatives. Well, let's study only the first derivative in this specific case. So f prime of x is equal to, okay, so we're looking at the function 3x cubed minus 2x squared. We're going to apply all the rules that we have studied so far. So here we're going to have the derivative of 3x cubed is 9x squared minus 4x. Okay, so now what we want to study is f prime of x greater than 0, which means 9x squared minus 4x greater than 0. We can factor out x. We're left with 9x minus 4 greater than 0. So what we can do, well, you can also study greater than or equal to. It doesn't really matter. If you study the equal to, it's going to give you the points where the derivative is equal 0. Now, the first one is x greater than or equal to 0, and the second one is 9x minus 4 greater than or equal to 0, which means x greater than or equal to 4 divided by 9. Okay, so we're going to plot them with our usual graphical representation. Here we have 0. Here we have 4 divided by 9. Okay, x greater than or equal to 0. It means that the derivative is positive here and negative here. X greater than or equal to 4 divided by 9. It means that the derivative is positive here and negative here. Now, we're studying the signs, so in this case, both elements are negative. So here, this is f prime of x greater than 0, greater than or equal to 0. So it means that the derivative is positive here, negative here, and positive here. Now remember that when the derivative is, and positive here. Remember that when the derivative is positive, then the function is increasing. And when the derivative is negative, then the function is decreasing. So if here we try to represent f of x, it means that it's going to go up here, it's going to go down till 0, it's going to reach a maximum, it's going to go down here, it's going to reach a minimum, and then it's going to go up again. So if you want to determine the maximum and the maximum is going to be the point 0, 0, then the minimum is going to be the point, well, let's call it with a different notation. I'm going to call it capital M, uppercase M, and lowercase m. So this is going to be 4 divided by 9. Well, you have to plug in 4 divided by 9 in the expression of the function. I computed this for you. It's minus 32 divided by 243. It's a number between 0 and 1. Minus 1 and 0. So it's minus 32 divided by 243. The value itself doesn't really matter, but what I'm saying is that I'm going to redraw the plot here. So first of all, we studied that the domain is the entire set of real numbers. We found the intersection in 0 and 2 divided by 3. We said that if x is greater than 2 divided by 3, the function is positive, and if x is less than 2 divided by 3, the function is negative, except for in 0 where we have the intersection. We studied the limits here and the limits here. this one here is a maximum. And somewhere here we have 4 divided by 9, which is the minimum. Now the intersection in 4, the value of the function is minus 32 divided by 443. So it's going to be approximately here. This one here is going to be the minimum of the function. And we know that the function increases to here, then it decreases to the minimum, then it increases again, and it goes up to plus infinity. Let me redraw it. Okay, something like this, where this one here is the minimum. Now, if you want, you can also study the second derivative. In this case, it would be pretty straightforward. I'm going to do it. We're not going to do it every time, but for some specific functions, it might be important to determine the convexity of the function. So if we have the second derivative of x, this is going to be, it's the derivative of the first derivative, so this is going to be 18x minus 4. So f second greater than 0 means that 18x minus 4 is greater than or equal to 0, which means x is greater than or equal to 4 divided by 18, which is 2 divided by 9. So this means that if this is 2 divided by 9, the second derivative is going to be positive here and negative here, which means that f of x is going to be concave here and convex here. Well, we kind of already knew that, because if you look at the function from minus infinity to some certain point between 0 and 4 divided by 9 is concave, and then it becomes convex. Well, this is the flex point, and this last part of the study tells us that it's somewhere 2 divided by 9. So here we're going to have a point where the convexity of the function changes. So first the function is concave, and then it becomes convex. Okay, that's the full study of a function. This one here was relatively simple because it's a simple polynomial, but it has all the elements of the study of the function. So we look at the domain. In our specific case, it was simple because it was the set of real numbers. We look at the intersections. We look at where the function is positive or negative. Now, in practical applications, 2 and 3 can be done at the same time. Because if you study the points where the function goes from positive to negative or negative to positive are also the intersections with the x-axis. We study the limits. In some specific cases, you might want to study the limit for x that converges towards finite values when we are at the border of the domain. For example, in this specific case here, y equal log of x minus x squared, the function is only defined between minus 2 and 2, so we're not going to study the limit for x that goes to infinity. We're going to study the limit for x that goes to minus 2 and the limit for x that goes to plus 2. And then we study the derivative. The first derivative is important to determine where the function increases or decreases. We had an intuitive idea already because of the regions of the plane where the function is defined and the regions of the plane where the function is positive or negative. But studying the first derivative also tells you where the maximum and the minimum are. In our case, in 0 and 4 divided by 9. And if you really want, you can also study the second derivative, so you can study where the function is concave or convex. We still have half an hour, so what we're going to do is a couple of other examples that are a little bit more challenging. The complexity is going to increase step by step. So we're going to do example 2. It's going to be, again, a rational function, but in this case, we're going to include a denominator. So it's 2x minus 1 divided by x minus 3. Okay, so the domain now is not that simple because the denominator has to be different than 0. So what we're going to do is study x minus 3 not equal to 0, which means that x cannot be equal to 3. So the domain is all the x's in R such that x is not equal to 3. Some people would also write it x minus 3. Now we look at the intersections. So first we're going to put x equals 0. Well, now this is pretty straightforward because y is going to be equal to 0. 0 minus 1 divided by 0 minus 3, which is equal to 1 divided by 3. So the first intersection is going to be p equal 0, 1 divided by 3. Now we're going to impose y equal 0, which means that 2x minus 1 divided x minus 3 is equal to 0. Now this one here, so we have to solve 2x minus 1 divided x minus 3 equals 0. Now x minus 3 cannot be equal to 0 by definition because it's the denominator. So we know that x minus 3 is not equal to 0 because otherwise f of x is not defined. So what we have to study is simply 2x minus 1 equals 0, which means 2x equal 1, which means x equal 1 divided by 2. So the other point, I'm going to call it q, is equal to 1 divided by 2, 0. Now we want to study when the function is positive or negative. So f of x greater than 0. So what we have to study is 2x minus 1 divided by x minus 3 greater than 0. Now we're going to do numerator and denominator. So here we want to study the numerator greater than 0. So 2x minus 1 is greater than 0. Now it means that x is greater than 1 divided by 2. And then the denominator, it's x minus 3 greater than 0, which means x greater than 3. I'm going pretty fast because I think that this is pretty straightforward for many of you. So here we have the numerator. So 1 divided by 2 is on the left of 3. The numerator is positive when x is greater than 0 and negative otherwise. The denominator is positive when x is greater than 3 and negative otherwise. Now, we're studying the sign of a fraction. So if both numerator and denominator are negative, then the entire fraction is going to be positive. It's going to be negative here and positive here. So this is f of x greater than 0. So we can already put something on our plot. So we know that the function is not defined in 3, and we know what the intersections are. So for x equal 3, the function is not defined. I'm going to draw a straight line, which is the asymptotical value. Then we know what the intersections are. So 0 in x equals 0, it's 1 divided by 3. And we know that the function intersects the x-axis in 1 divided by 2. So we have an intersection here. Well, it's not really on scale, but that's fine. Now we know that the function is positive for x greater than 3. So this is 1 divided by 2. We know that the function intersects in x equal 1 divided by 2. It's negative in between 1 divided by 2 and 3, so it's not going to show up in this part of the plot. And then it's going to be positive for x less than 1 divided by 2. So it is important, it is not necessary, but it's important to do this kind of graphical representation because you can somehow constrain where the function is going to go when you try to plot it. Okay, well, let's try to do the limits. So we're going to do the limit for x that goes to minus infinity of, we said 2x minus 1 divided by x minus 3. Well, no matter if the x is positive or negative, well, the way we generally do it is we factor out, we didn't really review the limits, but we generally factor out the x with the higher exponent. So in this case it's x power, so in this case it's x. So what is left is 2 minus 1 divided by x, and then x times 1 minus 3 divided by x. If you do the math here, you get 2x minus 1 and x minus 3. Now this part here, for x that goes to infinity, it goes to 2, and this part here goes to 1. Well, I should be a little bit more precise. I knew that this was going to happen, that I was going to delete everything, but let's try to give a better explanation. 2 minus x and 1 minus 3x. So if let's do plus infinity first, so we don't have to worry about the sign. In this case, it's actually the same, so it doesn't really matter. So if x goes to plus infinity, then 1 divided by x goes to 0. So 2 minus 1 divided by x goes to 2. And then 3 divided by x goes to 0, so 1 minus 3 divided by x goes to 1. So this quantity here goes to 2 divided by 1, so the limit is equal to 2. And then if we do the limit for x that goes to minus infinity, it's exactly the same. So it goes to 2. So somehow the function, I'm going to draw the limit in a different color. Somehow the function is going to converge to 2 here and 2 here. We can also study the limit of the function for x that goes to 3 minus and 3 plus. So we're going to converge to 3 from the left and to the right. So let's do x that goes to 3 plus first of f of x. Well, here we just replace it. So this is going to be the limit. Oh, well, sorry. Let's simply write the expression of the function. 2x minus 1 divided x minus 3. Well, we just replace it. This is 5 divided by 0 plus, because we're approaching from the right, so this is going to be plus infinity. And then the limit for x that goes to 3 minus of 2x minus 1 divided by x minus 3 is equal to 5 divided by 0 minus, so this is minus infinity. This happens very often when you have rational functions and there's a denominator. There's an asymptotical value. The function goes either to plus or minus infinity. To help you with the sign, you can actually use where the function is positive or negative. So the function is going to go here and here. So we already have a sense that the function might have this trajectory here and this trajectory here. So it's going to converge on the left from 2 from the bottom and on the right to 2 from the top. But we can study the derivative, and by studying the derivative, we're going to figure out all the remaining details. So we're going to compute f prime of x. Well, the function is written, well, I'm going to write it here just in case. Well, we have the denominator, which is going to be x minus 3 squared. And then here we have the derivative of the numerator times the denominator minus the derivative of denominator, which is 1 times the numerator. So what we get is 2x minus 6 minus 2x plus 2 divided by x minus 3 squared, which is, minus 1, plus 1. So this is minus x plus 1 is minus 5 divided by x minus 3 squared. Now this is interesting because so f prime of x is equal to minus 5 divided by x minus 3 squared. And we want to study where the derivative is actually greater than or equal to 0. Now, minus 5 is always less than 0, so the numerator is always negative. And then x minus 3, no matter which x we're dealing with, and then minus 3 squared is always positive. So essentially, let's write it this way. The numerator is always negative, and the denominator is always positive, except in 3 where it is not defined, of course. So it means that f prime of x is always negative in the domain of the function, of course. So f of x is always decreasing. Well, we shouldn't be surprised given the behavior that we suppose that that function would follow, but now we can plot it. So I'm just going to replot what we have already done before. So here we have the intersection in 1 divided by 3. Here we have a point where the function changes the sign is 1 divided by 2, and we have an asymptotical value in 3. It's not in scale, but that's fine. And the function is always decreasing. So we know that it starts somewhere here in 2, or close to 2. Then it's going to cross 1 divided by 3, cross 1 divided by 2, and converge to minus infinity here. So essentially we have this kind of behavior here. I'm surprised how well I actually drew it. And then it's going to go to 2 here from the top, starting from plus infinity, so it's going to look like this. Now, it's not in scale, but that's how the function looks like. And this is a pretty common behavior for when you have a fraction like this. Okay, so it takes about 10 minutes to do one function, so we probably have enough time to do 2 more. I would like to do one with the exponential and one with the log, and then I'm not sure if we will have enough time to do the trigonometric function, but this should be pretty straightforward for many of you. So we're going to do example 3. The function in this case is f of x equal e power 1 minus x divided by x squared minus 1. These exponential functions are very important in statistics because most of the probability distributions that we're going to look at are actually Gaussian distributions that are built using the Gauss function, which is an exponential function. So we're going to spend a little bit more time on this one here. Well, here we have to study the domain. We know that for the exponentials are defined for all the values of x as long as the exponent exists. But then here we have to determine that the values of x are such that the denominator is not equal to 0. So this is going to be x, which is not plus 1 or minus 1. So the domain is equal to all the x in R such that x is different than plus or minus 1. Some people might study if the function is odd and even, but this is not necessary in many applications because you're going to find out when you plot the graph. It's not going to if you can determine if it is odd or even from a simple inspection of the function, then it's great because you know what to expect. But otherwise, it's not necessary. Now we're going to study the intersections. So we're going to put x equals 0. Well, now, if x is equal to 0, we get e power 1 minus 0, which is e, divided by 0 minus 1, so it's minus 1, so we get minus e. So the first point to put on the graph is going to be 0 and minus e. Now, If y is equal to 0, it means that e power 1 minus x divided by x squared minus 1 is equal to 0. Now again, we know that the denominator cannot be equal to 0 by definition of domain of a function, so e power 1 minus x has to be equal to 0. But this is an exponential function, and exponentials are always positive, no matter what the argument, the exponent is. So this never happens. So there are no intersections with the x-axis. So it means that either the function is positive everywhere or negative everywhere. So what we're going to do is study f of x greater than 0, which means that we have to study e power 1 minus x divided by x squared minus 1 greater than 0. Sorry, I said something wrong here. This is valid. What I said would be right if the function was defined in an entire set of real numbers. So if the domain of the function is R, and you don't find intersections with the x-axis, then the function is either positive or negative in the entire domain. In this case, we have the domain is not continuous. You have some points where the function is not defined. So the function might be all positive in one part of the graph and entirely negative in another part of the graph without having intersections with the y-axis. I'll give you a quick example of this. This is not the function that we're studying, but if the function is not defined in this domain here, the function could be positive here and negative here. It still doesn't have any intersection because the way it changes the sign is to go from minus infinity to plus infinity. Even a function like this, 1 divided by x, this doesn't have any intersection with the x-axis, but here the function is negative and here the function is positive. So what I said before was not completely correct. So what happens here is that we want to study where this fraction is greater than 0. Well, we know that the numerator e power 1 minus x is always positive. Now we have to study the denominator x squared minus 1 greater than 0, which means that well, the associated equation is x squared minus 1 equal to 0, which means x equal plus or minus 1. We have already done it because that's how we define the points where the function is not defined. So this parabola is positive when x is less than minus 1, and it's positive when x is greater than 1. Okay, so we can plot something in the Cartesian plane. Now, we know that the intersection is 0 minus e, so it's going to be somewhere here. Minus e would be minus 2.71. We know that the function is not defined in minus 1, and it's not defined in plus 1. So the function is, I guess I didn't finish this part here. We have the numerator is always positive, the denominator is positive, it's positive for x greater than 1 and x less than minus 1, and it's negative otherwise. So the function itself is, I'm going to try to save some space here. So the function itself is positive for x less than minus 1, it's positive for x greater than plus 1, and it's negative in between. So it's going to be negative here, it's going to be positive here, and it's going to be positive here. We can study the limits. So here we can study the limit for x that goes to plus infinity of e power 1 minus x divided by x squared minus 1. Now, e power 1 minus x for x that the exponential is going to dominate the polynomial, so this is equal to the limit for x that goes to plus infinity of e power 1 minus x. Now, x goes to infinity, which means that this quantity is going to go to 0, so the limit is going to go here. Then we study the limit for x that goes to minus infinity of the same quantity. Again, it only matters what the exponential does because it grows faster than any polynomial. So in this one here, we're going to get the e power plus infinity because there's a minus here. So this is going to be plus infinity. So we know that the limit is going to go here. We want to study also the limit for x that goes to minus 1 and plus 1. So the limit for x that goes to minus 1, we should do minus 1 plus and minus 1 minus, but we already know that there's an asymptotical value. So if we find out that it goes to infinity, there's no reason to study the signs because it's going to be obvious by where the function is positive or negative. Well, in minus 1, this is going to be e power 1 minus 1, which is e power 2, divided by 0, which means that it's going to go infinity. So it's plus or minus infinity, because this is going to be 0 plus or minus. And it's actually the same for x that goes to plus 1. Sorry. This is e power 0, which is 1, divided by 0 plus or minus. So this is going to be plus or minus infinity. Now, in this specific case, once we study the derivative, it's going to be obvious what the function is going to do close to these points. But in general, oops. But in general, if you want to study the limit, you're more precise. Here we have an intersection. Here it's going to go again here and here. Again, we already have a sense of what the function is going to do. It should be something that goes here, then there's a minimum somewhere, then we go here, and then we go here. But if we study the derivative, we should find that we have some maximum and minimum. We're going to see actually that the maximum is not here in e, it's going to be somewhere between 0 and 1, in minus e. So we're going to study the derivative very quickly. So we have, oops, we have f prime of x. Okay, so here we have a denominator, so this is going to be x squared minus 1 squared, and then we have the derivative of the numerator, which is minus 1 times e power 1 minus x times x squared minus 1 minus e power 1 minus x times the derivative of the denominator, which is 2x. So we can factor out minus e power 1 minus x, and here we're left with x squared plus 2x minus 1 divided by x squared minus 1 squared. Now, we want to study when the derivative is positive. Now, this quantity here, I'm going to simplify it a little bit. because this quantity here is always positive, except for in plus or minus 1 where it's not defined. This quantity, damn it. This quantity here is also positive by definition. With the minus sign, it's always going to be negative, so it only depends on the sign of this quantity here. So what we can do is simply study x squared plus 2x minus 1 greater than 0. Well, I'm going to do the calculations pretty quickly. So here we get that the two solutions x1, 2 are minus 1 plus or minus the square root of 2. So this quantity is going to be positive when x is less than minus 1 plus the square root of 2 and n is greater than one. I did it wrong, sorry. X less than minus 1 minus the square root of 2, and x greater than 1 minus 1 plus the square root of 2. Now notice that there's a sign here, so this is going to change everything. So f prime of x is positive when x is in between minus 1 plus the square root of 2 and minus 1 minus the square root of 2. You can check the calculations later if you want, but essentially we have that the function decreases. So it's positive here, it's negative here, and it's negative here. So it means that f of x decreases first, and then it goes up, and then it decreases again. And here we have the minimum and the maximum. Now you see that the square root of 2 is larger than 1, so this quantity is actually positive. So the maximum is not in 0. We're not going to compute exactly the maximum and the minimum. We're just going to plot the function. Okay, so we said we had an intersection is minus e. We had an asymptotical value in minus 1. We had another asymptotical value in 1. So the minimum is in minus 1 minus square root of 2, which is approximately here. And the maximum is in minus 1 plus the square root of 2, which is approximately here. So the function, the limit was plus infinity, so it goes down and then it goes up. And then here it was minus infinity, so it goes up and then it goes down. And then it starts here and it simply goes to 0. So this is how the function looks like. Approximately. I was trying to highlight it with the green, but it didn't work out. Anyway. Okay, I'm going to do quickly one more example. So this is example 4. So f of x is equal to x plus 1 times the log of x plus 1, natural log, minus 2. Now the domain in this case Well, the argument of the log has to be positive, so x plus 1 has to be greater than 0, which means that x has to be greater than minus 1. So the domain is the set of real numbers such that x is greater than minus 1. Then we want to study the intersections. So first we impose x equals 0. Well, then y is going to be equal to 0 plus 1 is 1 times the log of 1 minus 2, but the log of, so this would be 1 times the log of 1 minus 2, but the log of 1 is 0, so this is minus 2. So we have a point P equals 0, minus 2. I would like to try to study this function without well, let's first delete some part of the plots. Add some constraints. So in minus 1, the function is not defined. And it's not defined for any value less than minus 1. So here the function doesn't exist. Now, if x is equal to 0, then the intersection is here in minus 2. Now, we should study the sign, f of x greater than 0. Well, this means that we have to study x plus 1 times the log of x plus 1 greater than 2. Well, this can be challenging, so let's see if we can study the function without studying the sign in this specific case. So what we can do is we can do the limits. The limit for x that goes to plus infinity, this is the easy one, because the function is x plus log of x plus 1 minus 2. So this goes to infinity, and this goes to infinity, so the product goes to plus infinity. But then we also want to study the limit for x that goes to minus 1. And we can only get to minus 1 from the right. Now, this quantity here goes to 0. So this quantity here goes to minus 2. So the function converges to some point minus 1, minus 2. Now, if we can study the derivative, and we know that it goes here. So if we can study the derivative, we can draw the function very easily. So we're going to do f prime of x is equal, well, this is the derivative of a product. So this is 1 times the log of x plus 1 plus x plus 1 times the derivative of the log, which is 1 divided x plus 1. So this part can be simplified. So this is log of x plus 1 plus 1. So f prime of x is greater than 0 when the log of x plus 1 is greater than minus 1, which means x plus 1 greater than e power minus 1, which means x greater than 1 divided by e minus 1. So the minimum is in 1 divided by e minus 1. So we're going to draw the function. It's not defined here. the limit goes to this point, -1, -2. The function also goes through this point, which is 0, -2. It goes to plus infinity, and we have a minimum somewhere here, which is 1 divided by e minus 1. So the minimum is here, and then the function increases. So here I should have said f prime of x is greater than 0 when x is greater than 1 divided by e minus 1, which means that f of x is increasing so the function goes up here and it goes down here. But again, we're starting from -1 because the function is not defined otherwise. So that's the graph of the function. Now, I did it pretty quickly. We're probably not going to look at functions in this form in the rest of the class, but I just wanted to give you an additional example. Okay, I went over by 5 minutes, so I'm going to stop here.